Hello and welcome to BIRKBECK online. We are looking at the subject of renewable transport, the synthesis of renewable gases and liquids for the energy and transport sectors. This is part of the module Energy and Climate Change, and my name is Jo. We're now going to zoom in and look a little bit more closely at transport. This realistic projection from DNV-GL shows that petroleum oil will continue to fuel a majority of transport. The effects of electricity, hydrogen gas and biofuels will only start to grow greatly after about 2035. The reason why fossil fuels are still very significant for transport is because of the energy density in these fuels. More energy is packed into a smaller space, and this is important when you are carrying goods and people. With cars, which are smaller and often make shorter journeys, battery electric vehicles will become more popular and more widely sold, and as time goes by will become relatively cheaper than a comparable internal combustion engine vehicle. ICE vehicles usually burn diesel or petroleum gasoline. The decarbonisation solution for cars is clearly battery electric. But what about freight? That is, the vehicles carrying goods long distances. Currently, trucks and buses are responsible for a very high proportion of greenhouse gas emissions in the transport sector. It's clear that some focus should be placed on dealing with this part of transport. Despite the fact that battery technology is improving, it will still take some time before long-haul, long-distance journey battery electric vehicle trucks to become cost competitive. For these to be successful, there needs to be a wide network of fast charging or supercharging for these larger vehicles. Converting transport to electric drive will be very successful, but there will be a large percentage that is unreachable by battery electric technology. This missing 40% needs some work. There are a number of proposals for alternatives to battery electric vehicles, particularly for heavy-duty trucks and lorries. One of the key fuels recommended for long distance and freight transport is hydrogen gas. So now we're going to take a little look at hydrogen. Most recent projections and proposals include hydrogen and other renewable gases. This Sankey diagram from the Energy Transitions Commission gives electricity the main seat at the table, but shows that hydrogen is an important secondary source of energy. Hydrogen is by no means a new energy fuel. For decades, town gas was delivered to people's homes. It was made from coal. The large structures that stored the gas, gasometers, can still be seen in various cities. Hydrogen is also in use in other parts of the economy. For example, in the refining of petroleum and also in the manufacture of ammonia for fertilizer. It is also important in one of the key technologies for manufacturing iron, and it is a key feedstock for the chemical industry, quite frequently through the synthesis of methanol. Hydrogen today is mostly sourced from fossil fuels, but also partly from byproduct hydrogen, waste from other technology and chemical processes. The demand for hydrogen will continue to increase, and this will be across the economy, industry, buildings, and in transport. And it is important to notice that hydrogen will be used to make further fuels. This will be very important for the aviation sector, as it is not anticipated to be able to fly large planes using electricity. The energy density of hydrogen will not be sufficient for large planes, and so hydrogen will be used to make higher energy density synthetic fuels. Notice too that this ETC modelling includes energy storage. One of the key aspects of making gas is that you can use electricity to make gas and then store the gas until it's needed because there's no wind and it's dark. Gas can be stored for months at a time and so can provide buffering of energy supply and demand across the seasons. Although grid-scale batteries can assist with offsetting power demand and supply on a daily basis, at longer time scales, gas will be more important. In this diagram, which discusses using excess renewable electricity to make gas as a form of seasonal storage, you can see that hydrogen and methane are both important. Everybody is talking about hydrogen, but what kind of hydrogen? Truly green hydrogen will be made mostly by electrolysis, that is, the splitting of water by the use of renewable electricity. Most industry communication at the moment is about blue hydrogen. This is either the steam methane reforming, or SMR, of natural gas, or the gasification of coal, but both of these technologies would need to be accompanied by carbon capture and storage in order to be acceptable in a low emissions economy. Grey hydrogen would be SMR or gasification of methane or coal, but without the carbon capture element. Turquoise hydrogen is a definition that includes pyrolysis of methane, where the hydrogen would be released from the methane without the carbon being turned into carbon dioxide. The carbon would become black ash, a solid that could be buried. Calculations of the cost of producing hydrogen from a range of sources vary widely. However, as power becomes cheaper, hydrogen also becomes cheaper, as can be seen in this chart, showing a contrast between locations with high costs of renewable power and low costs. Electrolyzers become more cost efficient the cheaper the electricity they use, but also the longer they are in use in every year. And so you should anticipate electrolyzers and wind farms, or electrolyzers and solar power plants, to be connected without supplying electricity grids, so that the electrolyzers can run all year round. And now for some chemistry. In simple terms, power to X, meaning use renewable power to make some chemical, has three main branches, each of them involving hydrogen. Hydrogen can be used on its own as a gas. It can also be reacted with nitrogen to make ammonia, or it could be reacted with carbon dioxide to make methanol, which would be a chemical precursor, or to make electric fuels or electrofuels, possibly from methanol or directly. And in addition, hydrogen can be reacted with carbon dioxide or carbon monoxide to make methane. Natural gas is 80 to 95% methane. So renewable methane made through the power to X technologies could be a direct replacement for natural gas. These three categories of power to X have multiple applications. Methane, methanol, and other synthetic fuels can be used for power generation, as chemical feedstocks, and as making carbon neutral synthetic fuels. Hydrogen can be used directly for mobility. It can also be used for power generation as a chemical feedstock. It can also be burned directly to provide heat. Ammonia is currently used as a precursor for fertilizer and as a chemical feedstock. In the future, it is likely to be more widely used as a carrier for energy. One of the important things to note is that methanol made from hydrogen can be very useful as an input chemical to other processes that make very useful fuels. You can make renewable gasoline from methanol. You can also make dimethyl ether, or DME, which is a fuel which is gaining popularity. You can also make oxymethylene dimethyl ethers, or OMEs, and there is work being done on using these to replace a certain proportion of diesel fuel. As OMEs have quite a lot of oxygen in them, they can burn very cleanly. And here you can see a comparison of burning OMEs against diesel. One of the problems with diesel is that it burns with a smoky flame, as the hydrocarbons are long chain. This is a major factor in damaging air pollution in urban areas. By choosing to burn cleaner fuels, we can partially resolve air pollution issues. Although a number of companies are currently studying the use of OMEs, their synthesis is still under development. Efficiency and the side byproducts need to be resolved. At first glance, it may appear to be inefficient to capture carbon dioxide and pump it underground to make sure it does not go into the atmosphere. But this technique of CCS is likely to result in hydrogen, blue hydrogen, remaining quite cheap compared to other options. CCUS is a term used to mean carbon capture, utilization and storage. The utilization part means that carbon dioxide is being used in the synthesis of new fuels. As these synthetic hydrocarbon fuels will be burned, this carbon dioxide will end up in the atmosphere. So it is not fully renewable or sustainable. However, it displaces the need to mine some hydrocarbon fuels. In other words, instead of pumping more oil, we can make some oil from carbon dioxide that would otherwise have been thrown into the sky.